There are many formulas that you can use for simple harmonic motion and calculating various things. I have chosen two that I think are very common and very useful, very straightforward. But again, if you read our book or any physics book, you could see, like I said, several different kinds of manipulations on simple harmonic motion. If we are looking for something with a spring, like a shock absorber in a car or a bungee cord or something like that, and we're looking for the period in the sense of, the spring going back and forth like this through the equilibrium point from A to negative A to back to positive A. If we're looking for that period and that frequency, we could use this formula right here. And so let's say that we have the car, the occupants weighing 1,400 kilograms, and the shock absorbers. The shock absorbers have K values of that. And we're wondering what natural period and frequency will have the car have when it hits a bump. And we need to talk about that in a minute too, about that natural oscillation that occurs when energy is imposed on the system. So to find the period there is a pretty simple formula. And we're just going to take a little plug and chug action going on there. And the K value of 6.5 times 10 to the 4th meters. Okay, so if you pop that into your calculators, you should get 0.922 seconds. And that's the time, of course, again, to go from A to negative A back to positive A from our pictures. And then our frequency is 1 over the period, and so we get 1.08 hertz. And again, just to visualize what that means, it's how many cycles per second. So what's happening when you count 1 second? How many times is it going from A to negative A back to positive A? How many times is it doing that in a 1 second period? And so you can use the units of 1 over seconds, but most commonly is hertz. All right, so if we're talking about a pendulum, again, a variety of different formulas that you can use for this, but this one I think is pretty straightforward. A couple of things to note with this is that the mass doesn't matter because the restoring force will be larger as the mass is larger, and those two will cancel each other out. The amplitude also doesn't matter because the longer the distance you have to cover is matched by a larger restoring force and thus a larger acceleration. So the amplitude doesn't matter either, which might come as a surprise, but there it is. So this is a really, I think, a straightforward formula for using or finding the period for a pendulum. And again, remember going from, say, a negative A, here's the equilibrium point, to a positive A, and then back to a negative A or something like that. All right, so we can do a couple of examples here. If we have this first one here, we have the period, the frequency of a 10-meter long pendulum at sea level. Because it does depend on the acceleration due to gravity, we will go 9.81. It's technically could do more significant figures than that, but we're just going to go ahead and use that at sea level. So we'll go 2 pi. My pendulum length is 10 meters. Acceleration due to gravity. And we're going to calculate that at 6.34 seconds. And then, of course, the frequency would be 1 over 6.34 seconds. And we would get 0.158 hertz. Okay. Another kind of problem using the same formula that you could come across is, let's say that you have a pendulum and has a period of 2 seconds. And so we have that period of 2 seconds. And now the question is going to be, well, maybe we've taken this pendulum clock up on the top of Mount Everest, and the gravitational constant is a little different. Now, honestly, that's not going to make much of a difference going up to the top of Mount Everest. But you will note that this G is going to make a difference. because the bigger the g is, the smaller the period, and as the g goes down, the acceleration and the gravity goes down, the longer the period is. So your clock, if you had a pendulum clock, would actually slow down the higher that you took that. And that might be something we look at as a little extra credit thing, because Einstein had something to say about clocks running slower or faster near or far from a mass. So maybe we'll take a look at that as well. But in any case, you can see how the g is going to make a difference here. All right, so go ahead and solve for g, and make sure that you can do that. You basically end up with here, you remember that algebra? It's kind of annoying. You end up basically with 1 over pi squared there on the bottom. So just make sure algebraically that makes sense to you. And you end up with 8.72 meters per second squared. Now you have to be pretty high away from the Earth for that g. In fact, you probably have to be as high as the International Space Station for that g to be valid. But there you have it. Okay, the other thing that we want to talk about in this video is resonance. And when we talked about the shock absorber hitting a bump and just having this natural oscillation, natural frequencies happen when an object is disturbed. It's going to vibrate at its own special set of frequencies. If we pluck a guitar string, how heavy is that guitar string? What kind of vibration is going to happen? Depending on the object's elasticity, its shape, its mass, its natural frequency is going to be determined. So it has natural frequency or frequencies, F sub naught. A natural frequency is one at which minimum energy is required to produce that vibration. Now, we can also impose a force by just applying that force at a certain frequency. So we could apply a force at any point if we want. But let's say that what we do is we take that applied force and we make it equal to the natural frequency. And so you get something called constructive interference, which we'll talk about a little bit later, and our amplitude and thus our energy is at a maximum, and that's called resonance. And there's several different examples that you can take a look at with resonance if you look them up. If we were in class right now, I'd talk about a lot more of them, but let's just do a couple of them here. If you've ever seen someone singing, or I don't know if that's humanly possible, I understand it is, or a note that's being played that breaks a glass, that's because resonance is set up in it. A soup bowl, if you've ever noticed as you walk with a soup bowl, your walk is pretty close to, your step is pretty close to the diameter of the soup bowl. And if you're not careful, you'll start seeing that splashing increase, and pretty soon the soup is over the edge of the bowl. Bay of Fundy is something else that you should take a look at. And okay, so the Bay of Fundy, like I was saying, is between Nova Scotia and New Brunswick, and you'll see it if you Google it. The tides are unusually high because the length of the bay is equal to the waves that come in, and there's resonance that's set up, and it just becomes higher, like a soup bowl that you'd be carrying. I think this might be anecdotal, but soldiers, they will have soldiers break the march when they go over a bridge, because if their march happens to match the natural frequency of the material in the bridge or the construction of the bridge, you could potentially collapse the bridge. Definitely want to watch the next video. There's a little bit more complication going on there with some low and high pressure twisting that goes on, but that also in its own sense is resonance. But resonance was set up in this Tacoma's Narrows Bridge, and definitely the video is worth watching. It's interesting that they were able to get footage of it, but the resonance was being set up over, I think it was hours of time. So they were able to go get a camera and set this up. Of course, this was a long time ago, so getting that apparatus up and going took a while, but the bridge was going for a while before it finally collapsed, so definitely want to take a look at that. Okay, so here this video, I guess I won't show you a video of it, but I don't know if it lets me. If you click on this, I guess I am going to start showing the video, but you can stop me at this point and just go watch the video. But notice that this resonance starts setting up. It's been setting up for a while. And then if you fast forward, you can see the end. And there's definitely more videos of this, more scientific explanations for it, but it's kind of crazy what you can get out of resonance. But I definitely encourage you to look up videos of the Bay of Fundy, other resonance videos that you can set up, and of course watch the next video.